All right, so we're going to talk more about Big O today because I think that's a topic that a lot of people need help with. So you have to think of Big O as worst case, right? So if you have a binary tree, an unbalanced binary tree, dot, 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 there, right? So if I've inserted the numbers from 1 to a million into a binary search tree, 1 million, there. Okay. If I just insert 1, then 2, then 3, then 4, then 5, it's going to be totally unbalanced like this. Okay. So you have to think of n as just being like some large number. And if I say, what is the time to search? If I say, what is the time to search this tree? You might be like, well, what if we're searching for 1? Right? It's order 1, right? Because you can find 1. You have to always think about what's the worst case. The worst case is, depending on how you look at it, either a million or, a million and one, right? If it's not found, it's technically one step worse than the last element. Either way, it doesn't matter. So the worst case is what we care about, not the best case. And so if we're searching for a million, then if you search for a million, then how many operations? 1 million. How many operations do you need to know to go down the tree? A million. Yeah, n, right? In this case, n is a million. The size of the data structure is a million, so order n, order million, whatever. Okay, so in this case, searching is order n. What is the time to insert into this tree? So worst case scenario again. Maybe you can insert 0. That's fast. Order 1. What is the worst case? What number, if you were to insert, would give you worst case performance? Pick a number. What number, were you to insert it, would give you worst case performance? Emma picks 1,000,001. Doesn't have to be 1,000,001, but that is a worst case number, sure. Doesn't have to follow the 2 million. Yeah, that's easy. Yeah, any number bigger than a million, right? Will give you an order n insert. And so a lot of people are used to saying, well, everything in a binary search tree is order logN. Wrong. Right? That guarantee only holds if you are using a balanced binary search tree. Fortunately, set, if you hashtag include set, it is guaranteed to be balanced. However, for Dungeon Delve, it is not. And in fact, it should not be. It should not be balanced. Because what you're doing in Dungeon Delve is creating a dungeon that mimics a binary search tree. Big O be confusing. That's why I'm lecturing on it today. Okay. So a lot of students make the mistake of trying to memorize. Like they get flashcards, like, all right, binary tree, login insert, login search, login delete. You can't. You have to understand the data structure, and then you can create the Big O from it. Do you guys understand? And so, like on the most recent quiz, I think I asked about linked list Big O time or something like that. And so if no set appears anywhere, assume unbalanced. In a quiz, I will say balanced binary search tree. But if I don't, if I just say a binary search tree, then it's order n, right? For basically everything. For basically everything. What is the... For this tree, in other words, everything's been inserted in order. What is the time to find the minimum element? What is the time to find the smallest element in a binary search tree that had everything inserted in order? From a binary search tree, we've inserted everything in order and it's horribly imbalanced. How much time does it take to find the smallest person in the binary search tree? Good. Yeah, it is order 1. And so even though this is an unbalanced tree, it's good at one thing and one thing only, and it's good at finding the minimum element. So if you insert everything in order, you have made a linked list, but with more steps, to paraphrase Rick and Morty. But it is good at one thing, and it is good at finding the minimum element, I guess. In general, though, let's talk about balanced binary search trees. So this would be a balanced tree. It's not full and complete, like some of the examples I gave are, but it's balanced. It's maybe it's a little bit unbalanced. Maybe had a few more guys on here. In general, the rule is he's got 4 kids to the left and 5 kids to the right. Yeah, that's close enough. The general rule is you can't have more than twice as many kids in one branch in the other branch. So that's fine. So maybe this one's not balanced here. Yeah, whatever. You get the idea. Like a tree doesn't have to be perfect. It doesn't have to be perfect. It can just be kind of perfect. As long as that 2-to-1 ratio is enforced, it's fine. This one's got a problem of 3 and 0, so it would need to do a rotation to balance it, but I'm not going to do that. So more than twice, so it is a ratio, yeah. Mm-hmm. So 4 on one side, 5 on the other side, it's a balanced tree. Whereas if I had this, one to the left, 5 to the right, this would not be a balanced tree. And so anytime you're dealing with a balanced BST, which again, you'll learn how to make these in junior level data structures. I'm not going to teach you guys how to do it here. It would do a rotation. And so it would rebalance the tree so that it is roughly even on each side. Okay. But you don't have to know how to do it, just know that it exists. Okay, so let's make a... There. So this guy's got 5 kids to the left, 5 kids to the right. This one's got 2 to the left, 2 to the right. 1, 0, 1, 0. Good enough. All right? Good enough. So, rotations is something physical like chemical bonds. No, a rotation is when you have a binary tree like this. So you got 5, 10, 15. And so rotation is doing pointer tricks. And you turn it into 10, 5, 15, like that. So that is a rotation. And so it'll balance the tree. Because here you can see it's got 2 kids to the right, no kids to the left. Here it's got 1 to the left, 1 to the right. And so whatever the incoming pointer is now going to be pointing at 10. 10's left pointer is going to be pointing at 5. So it goes like this. That's called a left rotate. And you don't need to worry about that because that is a junior level topic. But that's generally what happens. And so in case you're wondering how it balances itself, it'll do these, and it just does pointer stuff. It's like this points to this equals points to this equals this. Doesn't have to delete, doesn't have to new anything. Okay. And there's a lot of different ways of balancing trees. The one that most people learn is called red-black trees, which I think is what the standard library uses. There's also something called AVL trees, in case you're curious. AVL trees, and there's red-black and things like that that'll balance themselves, but are too complicated for this class. Okay. Okay, so let's talk about a balanced binary search tree. So if I were to insert into this tree, what's the worst case scenario? Insert is big O what? Yep. logN it is. Very good. Okay. Log base 2 if you care, but I don't care. All right. So insert is order logN. So like worst case would be like here, something like that. And so the number of levels you go down, level 1, level 2, level 3, level 4. The number of levels in a balanced tree is equal to the log base 2 of n. I think ceiling, something like that. Plus 1, I don't know, something like that. Basically, it's proportional to log base 2. And the big O of inserting and searching and deleting, we don't have to run through all these again. Because if you're going to search for something, if you're going to search for this guy, you have to go down a number of levels. The number of operations you do, go to the right, go to the right, go to the right, go to the right. The number of operations you do is equal to the number, the depth of the tree, right? And that's proportional to order log n. And so insert, search, and delete all order log n. All right, those are the basic things. Those are the three big operations we care about, right? Add something to a data structure, use the data structure, and delete from the data structure. Those are the three big things. But there's other operations as well. Like we just talked about min element, right? What is the big O of min element? If you want to find the smallest element in a binary tree, what is the big O of it? So David Thompson, why do you think it is n? Bazookian says 1. We got logN from Panu. We got n from Thompson. We got 1 from Bazookian. You guys want to defend your positions? So we have a balanced binary search tree. So what do you have to do? Doesn't it use an iterative? You could, if you wanted, you could do this. You could say for every integer x in binary search tree, because this is a binary search tree events, int min equals negative maxent, whatever. If max is less than x, max equals x. You could do it that way. This would be an order n operation, where you iterate across the entire binary search tree and find the biggest element. You could do it that way. You could do it that way. I wouldn't. If you want to find the smallest element in the binary search tree, it's going to be this node. Right? Because you start here at the root, and is there anybody smaller than the root? Yep, go to the left. Is there anybody smaller than that guy? Yeah, go to the left. Is there anybody smaller than that guy? Yep, go to the left. Is there anybody smaller than that guy? Nope. So there cannot be anyone smaller in the binary tree. So to find the minimum element of a binary search tree is log n, unless, Bazookian, you want to defend order 1. The root is not the smallest element. Yeah, that's what I'm saying. In that previous unbalanced one, if you have an unbalanced tree created by adding a sorted array, it'll be faster. Min is the leftmost node, so it's 1. How do you get to the leftmost node in order 1 time? Because the entry point to a binary search tree is the root, right? So to get to the leftmost node, got to go left, got to go left, got to go left. And vice versa. Yeah, so max element's going to be the same. It's going to be order log n. So what if the root is the min? Worst case scenario, Bazookian. Worst case scenario is in a balanced tree that this guy is going to be logN away. He's going to be log base 2 of n to the left. Okay. LogN is the number of levels. Yeah, every time you double the size of a binary tree, you add one more level to it. 1, 2, 4, 16, 8, 16, 32, 64. Every time you add a new level, you've doubled the size of the tree. And so for every doubling of the problem size, you have to do one more step. That's what log means. Log is the opposite. It's the opposite of 2 to the n. 2 to the n algorithms are really bad. 2 to the n algorithms mean for every one additional city that you're going to try to find a shortest path from, you have to do twice the work as before. And so it doesn't matter how powerful your computer is, you will very, very quickly destroy your computer, so to speak, using an order 2 to the n algorithm. Like maybe a computer in the past could do 17 cities. Maybe today we could do 40. Not a million, not a billion. And so order 2 to the n is intractable. Order log n is the opposite of this. Logarithm is the opposite of exponentiation. So for every doubling of the problem size, we only have to do one more step. It's really good. Log n is very fast. It's good enough for most purposes. Order n factorial, yeah. Shuffle, make every possible shuffling of a deck and find the one that's sorted. There you go. Do every possible shuffling of a deck. Find the one that is sorted. That is an order n factorial sort. Try every shuffle. It's terrible. Try every shuffle, pick the one that's sorted. Min value, struct node to current, while current left is not null, current equals current points to left, return current points to data. Yes, Bazookian, that is an order logN algorithm. That is not a order 1 algorithm. However, you are correct. Do people ever use big O slower than order n? Yeah, you got to. I mean, there are some problems that are intractable. There are some problems that there is nothing faster than order 2 to the n. It's called NP algorithms. So non-polynomial means exponential, right? In general. There is EXP also, but in general we talk about NP, non-polynomial algorithms. And there's a whole bunch of them. Chess, right? Othello. Traveling salesman problem. There's a bunch of these things that are exponential running time. So, yeah, you're right. Absolutely right, Ephraim. So, but there is a way of doing this in order 1 time. So that's why I was asking Bazookian, what's your algorithm for finding the minimum element in order 1 time? Anyone see any way of doing it? Grace says have a pointer to the minimum. Yes, that would work, except what if we deleted this? Then we'd have to kind of come back through here, and I mean that would be wrapped into the delete function, I guess, and it would still be order logN. Yeah, sure. Yeah, good. Yeah, good answer, Grace. Yeah, I'll allow it. I was just thinking you just kind of write down what the minimum element is. You know, you just have a variable in your tree class that holds the minimum element. But yeah, having a pointer would work too. And then if you delete it, then you just run through the tree again and find the newest minimum element. Sure. Yeah, I mean, it would slow down your insert and deletes. I was thinking about just a variable because that's just pretty easy. You just inserted something. Is that thing I inserted smaller than... But I mean, it still has the same problem. Like when you delete, you still got to retraverse the tree and stuff like that. But that wouldn't change the big O time. Do you guys see that? Like if you do a delete, like let's say I deleted 1. That's a login operation because you got to go through the tree to delete it. And now I got to update the minimum, right? So I now have to traverse the tree again, or maybe if I was smart, as I'm going down to delete, I just remember who the parent is. So, but let's say we do it dumbly. We delete the smallest element, then we retraverse and do it again. that would turn our delete into order 2 times the log base 2 of n. Right? So twice we're going to do logN work. However, does this matter to us? It's running twice as slow as before now. Do we care? In terms of big O, do we care? We do not care. It's still order logN. Okay. What we care about are changes that will turn our algorithm from logN into n, or n into n squared, or n squared into n cubed, or vice versa. We do care if we can get better performance out of it, right? So, yeah, Yui, it's a very good question. Like, do people use algorithms slower than n? And yeah, in general, for a lot of algorithms that I work with, the fastest, provably fastest running time is order n times log n. For a lot of the algorithms I work with. If you can get your algorithm to run in order n log n time, you're done. You're done. Unless you see some obvious way of like making it faster. If you can get your algorithm to run in order n log n time, is good. Right? Because most of the time you can't even beat order n, right? It's like order n is sort of the floor. And I mean that like in terms of like, well, you got to read the data, right? Like if you're going to be trying to find the shortest path between cities, you got to read the cities in, and that's an order n operation already. So in general, an overall program can't be faster than order n. This is sort of like the floor, because you got to process the data. You know, once it's in memory, then yeah, you can do an order logN search, order logN insert, order logN delete. But if you're talking in terms of an overall program, order n is because you got to look at everything. You know, find the best baseball player. You know, all right, we've got to read through all the baseball players, and you know, you got to touch everything at least once. And so, if you're doing all this stuff already, and then you just throw in like an extra login work or something like that, it doesn't matter, right? And so anything that's faster than order n, a lot of times we'll just call it free. You know, if it's, you know what I mean? Like, let's say you read in all the people, and then you do some login operation. This will take 1 million operations for 1 million people. This will take 20. 1 million and 20, right? 1 million and 20, who cares? You know, 2 million and 21, don't care, you know? And so, by and large, the target that I usually look for is that. So, for example, if I'm reading in all of the baseball players in Major League Baseball, and I'm putting them into a binary search tree, a balanced binary search tree, the overall algorithm will be order n log n. Why? Well, there's n players, and for each player, I have to insert them into a binary search tree. So that's n log n. And so if I do that, I'm happy with it. You know, like, I'm good. I could do better. I could do better than that. You know, like I could use a hash table. The unordered map that we talked about last time, that would turn it into order n. Okay. And so, you know, be 20 times faster. It's pretty good. For 1 million people, it's 20 times faster. It's pretty good. 2 million people, it's 21 times faster. It's pretty good. I'd probably do it. But like I said, in general, like once you hit n log n for your total program, that's oftentimes when we're like, it's good enough. It's good enough. Order n squared is even slower than n. Yeah, and order n squared algorithms are very common. And oftentimes there's nothing faster than order n squared, order n cubed, and before you start saying, oh, that sounds really, really slow, they're not. Right? Like, so there's different, what does it mean to be slow? Right? So if you have an order, let's say we're going to process 1 billion cities or 1 billion baseball players, whatever. We're going to have n is equal to 1 billion. It's a lot of baseball players, right? It's a population of China. Let's say we're going to try and find the richest man in China. I don't think it's Jack Ma anymore. It's the water bottle guy, I think, right? And so if I want to find the richest man in China, I can insert all of them into a binary search tree, which will take order in log in time to insert n people into a binary search tree. In times, I do log in work. And so if we just pull up a calculator and do a back of the napkin calculator, a billion log base 2 is 30. Okay. And so this is roughly 30 billion operations. If I use a hash table, unordered map, which we'll be talking about today, it'll be order in, so it'll be roughly 1 billion operations. And so it's a 30 times speed difference. Okay, I'd probably do it. You might need more RAM. Hash tables are, but it's significant, but it's not as significant as you'd think. Because let's say your CPU processes, what is it? Let's say you've got just to make the math easy. Say you've got a 3 gigahertz processor, and each hertz you do one operation. So this guy here would be 10 seconds. This guy here would be 1 second. Do you guys care? So if you want to write a program and it's going to analyze all the people in China, do you care if it takes 10 seconds or if it takes 1 second? Do we have anything faster than login except order 1? Yeah. Well, there's login, and there's login, right? But in terms of the common operations, in terms of the common operations, 1. What we're talking about. Do you have to run the program multiple times? How often, Mr. Frisbee, do you have to find the richest man in China? Why would you be doing that? You're writing like a newspaper article, maybe, or you're part of the tax department. I don't know. Like how often is it going to change? Right? That's that's actually a pretty pertinent question. How often is the richest man in China going to change? Daily? Maybe. Like with Elon Musk and Jeff Bezos bouncing back and forth. The end of every day, you might rerun it. I don't know. Doesn't seem like it would matter much to me, because like at the end of the day, you hit run. Does it take a second? Does it take 10 seconds? It doesn't matter. You run it once a day. Buy a faster CPU, like whatever. If it matters that much to you. Do most of the time we look into time complexity? Yeah. Space complexity also matters, though. Yeah. So in general, though, RAM is a lot cheaper than CPU. And so if you don't have enough RAM to hold records for 1 billion people, you buy more RAM, right? And so if you want to, my PC here has my PC here has 32 gigs of RAM. So that's enough to hold all of the people in China, probably. If there's 1 billion, as long as they're not using 30, maybe it's not. Maybe it's not, actually. I mean, it depends what records we're holding, right? Name, address, phone, social security, birth date. Like, yeah, I could actually run out of RAM. And so, but if I was doing that, like if that was my job, I would buy more RAM. Easy. So, so the question is, and this is not something I'm giving you the answer for, because I don't know. I don't know if 10 seconds versus 1 second is enough to matter to you guys. Like I'll tell you, in my professional career, I wrote an algorithm that I knew was unoptimized. But here's the thing, and it took 15 minutes to run. And I knew if I spent 5 or 6 hours optimizing it, I could get that thing down fast, like probably within a minute. But here's the thing, I ran that program once a year. So I never bothered. What I do is I'd run the program, it'd do all these SQL queries and grab all this data and do all these stats, and I would go to Starbucks and get a coffee, and I'd come back and it would be done. I ran it once a year and got paid $30,000 for running it once a year. Sure, my professional pride was a little bit like, I should probably fix it. But like your auto grader, like the auto grader, I could easily make it run twice as fast. But I don't, because I auto grade something, and does it take 5 minutes or 2 minutes? I run it once a week. Who cares? I don't care. So it's an opportunity cost situation. Yeah, programmer time is something to optimize for. And so even though I knew I could get it from 15 minutes to 1 minute, I ran it once a year. I didn't care. Or maybe if I had 5 projects I was working on, run it 5 times a year. It's still not enough for me to care. Right? So I would open up all 5 tabs. It'd be sitting there crunching the numbers. I'd go to the park. Come back. All the numbers are in. Done. But what I did there was something that my competitors all did by hand. They were doing tons and tons of mathematical computations by hand or in Excel or in calculators and things like that. I had a program that did it all for me. And so I had a huge competitive advantage in the world of statistics because I was a programmer. And so this is actually something I want all of you guys to understand. You don't actually have to go into computer science to be a professional computer scientist. You can get your degree in computer science, which I recommend. It's great. It'll get you a job anywhere in the world. But you don't have to do quote-unquote computer science. I wasn't being hired as a programmer. I was being hired as a statistician, more or less, to take data, tons and tons and tons of data, and process it, and clean it, and analyze it, and generate conclusions. And all of my competitors had to do it by hand, one way or another. And because I'm a computer science person, I wrote a program to do it for me. Once a year, I hit a button. So there you go. If it's working, don't touch it. Yeah, that was another thing. It's like if I were to rewrite the auto grader to be faster, it would actually break the grading on any of the homework assignments where it uses the current time. Because what I would do is I would cache the results of my program. Right now, it reruns my program every time it runs your program. And so, like I said, I can make it twice as fast by simply running my program once, saving the results, and comparing it against yours. But if any of the programs use something having to do with the current date and time, like Bridges Earthquakes, where it is pulling earthquake data in real time, I can't cache it. And so rather than have a command line flag or something like that, I don't know. I was like, whatever, I don't care. I don't care. So, login 1, it's close enough that usually you're just or not. So Frisbee is it depends. And so it does depend. If you're running this every minute, then yeah, you'd want to optimize this. Now let's talk about the other big O classes. So if we're talking about order in squared, how long is it going to run this analysis? Let's say that you write bubble sort, right? So let's say that you're a CSI 40 student. You're given the task of finding the richest person in China. You've got all these records, name, date, address, income. Okay, there. And you write selection sort or bubble sort, which is an n-squared sorting algorithm. How long is that going to take to run? Well, it's a billion times a billion. 1 billion times a billion is a big number. And then we can do 3 billion operations per second. So that's how many seconds. Divided by 60 gives us minutes. Divided by 60 gives us hours. Divided by 24 gives us days. Divided by 30 gives us months. Divided by 12 gives us years. It is 10 years. Do you guys see why big O matters? If all you do is change one line of code to go from bubble sort to quick sort, bubble sort is order n squared, quick sort is order n log n. You will go from 10 years to 10 seconds. Right? And that's what a lot of you guys found on the ELO assignment, which is that on the ELO assignment, if you had any inefficiencies in your code, like an n squared where it didn't belong, or you did a range-based for loop over the entire thing when you didn't need to, you would your time budget would get exploded, right? And so even though n and n squared are both polynomial, and polynomial is considered fast, you're talking about seconds versus years. And so the single most important optimization you can ever do in computer science, most of the time, is increase the complexity class, improve the complexity class of your algorithm. Find a place where it's order n, and maybe that's inside of a loop that is running in times, and so you've got an n squared thing in there, and maybe you can change that to logN because you're, like this is what a lot of the students on the ELO were doing, n times. There's n students, they were searching through the entire thing to see if there was a match, right? So a lot of students, like probably half the class, did this. Every time they inputted a student, they would go through the entire binary search tree for student x colon BST. That is a range-based for loop. It's going to go through the entire thing. If there's a match, die. And so that is n times doing n work. That is n squared. If all they did instead of that was use count, which searches the array, that would make the whole thing order n log n. Right? So even though that order n didn't look bad, and at the end I do an order n, but it's not within a loop or anything. So that one order n adds like 0.3 seconds to my running time. I don't care. If you're doing that order n operation inside of another loop for every student, check every student if there's a match, that will explode your running time. It'll explode your running time. And so that's the thesis of this class, right? Like this is why we're studying data structures, right? With a binary search tree, you can search a data structure in log n time. On a vector, you search it in n time. And even though they look very similar, when that's inside of another loop, you get crazy huge differences in performance. The single most important thing for most of your programs is the data structure you pick. You have to pick a data structure that matches your needs. Okay. Is it 375 years? Check the 2 to the n. Okay. All right, so let's look at order n cubed. Order n cubed. Again, these are very common algorithms, and they're not even considered slow. Like they're slower, but they're still polynomial. These are still poly runtimes. N squared, n cubed. They're all considered polynomial runtimes. We're not even talking about non-polynomial, which are horrible. These are still considered fastish. You know, order n cubed. If you need to, you got to do it. You know, order n cubed. You know, rent some time on Amazon's compute nodes. You know, whatever. All right, so order n cubed. So if we have a billion elements, that is a I lost track. Is that a billion? Thousands, millions, billions. Yes. Okay. Times. Damn it. 1 billion times big number divided by divided by 3 billion seconds. Divided by 60 gives you minutes. Divided by 60 gives you hours. Divided by 24 gives you days. Divided by 30 gives you months. Divided by 12 gives you years. And so this is thousands, millions, 10 billion years. 10 billion years. So watch out for those range-based for loops. You do a range-based for loop inside of a range-based for loop inside of a range-based for loop. Yeah. See you all at the heat death of the universe. Not quite. I think 10 billion years is still within the universe being alive, and it is possible you could actually solve that by, you know, renting compute time on Amazon EC2 nodes or something like that. You rent a billion of them. You know, I don't know if they have that many, but you could feasibly maybe cut that down to size. You know? And these are still the fast algorithms. So let's talk about I don't know, not a billion. Let's just talk about 50. Order 2 to the n. Just 50. You have an order 2 to the n algorithm, which generally these algorithms are brute force. Right? Like if you want to try every possible password, it's going to be an exponential. This is called non-polynomial or exponential runtime. So anytime you brute force a password, let's say you've got 26 possible letters for a password. There's more, but let's just say there's 26. If there's only one key, one letter in your password, it's 26 possibilities. If there's 2, it's 26 times 26. If there's 3 letters in your password, it's 26 times 26 times 26, or 26 to the third. Actually, that's not even exponential. That's not even that bad. But yeah, like if you brute force, like if there's 10 inputs and they can all be true or false, then it's 2 to the 10th power inputs. If you have 50 possible inputs, like if you've got let's say 50 if statements, and you're testing your code, you're writing tests for your code, and you want to try every combination of true and false for all the tests, that is 2 to the 50th power. Okay. So just for 50 if statements, which isn't that many in a program, right? 2 to the 50th is a number, right? Divided by 3 billion, divided by 60 to get minutes, divided by 60 to get hours, divided by 24 to get days, so it's 4 days. Not too bad. 4 days. Now let's just, increase it from 50 if statements to, I don't know, 70. We've written a few more lines of code, we got a few more if statements. It was a little slow to test before. Let's try it now. Every possible combination of true and false and all of our if statements. All right. So now it is 2 to the 70th divided by 3 billion divided by 60 to get minutes, divided by 60 to get hours, divided by 24 to get days, divided by 30 to get months, divided by 12 to get years. So it has gone from 4 days to 12,000 years. Going from 50 to 70. And if you want to try 80, just 10 more if statements, not a lot. Maybe we throw a lot of compute power at that, and we successfully tested our program that had 70 if statements. Wrote a few more. Let's do 80. Let's see how that works. 2 to the 80th power divided by 3 billion, divided by 60 to get minutes, divided by 60 to get hours, divided by 24 to get days, divided by 30 to get months, divided by 12 to get years. 12 million years. Just 10 more if statements. 2 to the 10th is 1,000. Ish. This is in human years, yes. Well, yeah. So you'd have to wait 12 million years for your program to test all 80 possibilities. This isn't this is not a large number. It goes from being like, yeah, you might want to wait that long. You add 20 more if statements, like, nope, maybe, and then it goes, really, no, With 2 to the n, it quickly becomes intractable. It quickly becomes too hard for even the most powerful computers to deal with. Try 100, right? 100 is going to be 1,000,000 times slower. So it'll be 12 trillion years. Just for 100 if statements, not that big. Okay. So what is the slowest, the absolute slowest? There is no absolute slowest, but the slowest you'll probably encounter is what I talked about before, which is order in factorial. Like where you randomly, well, you don't random. Try all permutations of a deck of cards, find the one that is sorted. So you take a deck of cards, you try every possible permutation, and one of those is going to be sorted. That's your sort algorithm. That's order in factorial. 52 possibilities for the first card, 51 for the second card, 50, 49, 48. Multiply, 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 multiply. So the running time of that would be 52. Factorial divided by 3 billion, divided by that to get minutes, divided by that to get hours, divided by that to get days, divided by that to get years. So it is going to be a big number. 1 times 10 to the 52 years. 1 with 52 zeros after it in years. It's a little bit worse. And that's only for 52. And it's 52 here. Not a big number. So, yeah, there's probably a better algorithm to sort a deck of cards than shuffling it a bunch of times. Okay, so let's go back to this. So let's go back to linked lists, maybe, right? So let's say that you've got a linked list. Doubly linked. Head. Tail. 7, 2, 9, 8. What is the running time to find the smallest element from a regular linked list? What is the big O? If you want to find the min element. The min element. The min. Same as max. Not going to go for both. It's obviously the same. You can actually do min and max at the same time if you want. That's how the standard library does it. You're like 90 years old. Your code's been going for 70 years. Here you are sending my pride and joy. Kid accidentally hits the power button. Why, you little... Yeah, in Seaside 26 a year ago, a student had a pathfinding algorithm running for 3 days, and I finally killed it. I'm like, it's supposed to run in a couple seconds, dude. He had big O problems, though. Yeah, so it'd be order n. Yeah, I agree. Because in order to find the smallest element of just a regular linked list, you create a temporary pointer here. And you go to the right, and you go to the right, and you go to the right, and you go to the right until you hit the end. And so if there's n elements in the linked list, you go to the right n times. Somebody's like, you go to the right n minus 1 times. Who cares? Or maybe you do go to the right n times. You stop when it hits null. Nobody cares. Nobody cares. Trust me. Is it order n minus 1? Nobody cares. Because it's like, are you going to do 1,000,000 operations or 1,000,000 minus 1 like no. And there's usually some sort of initialization stuff. Like you got to set temp equal to head, and we don't care. Just order it. Okay. So what big O did that student have? I think he had an order. I think he had an order n squared algorithm when it should have been order n, I think. Do you have his code still? Use it as a chance to show us what to not be good exercise for the class. Yeah, I could pull it out in a second, I guess. But let's talk about this. So yeah, to find the minimum element is order n. What if though I sorted the list? So sorting the list takes order n log n time. What's the running time to find the smallest or the biggest element in the list now? Camila's coming over at 6:30. Order 1. And so if you're just going to call min once, is it faster to sort it? Let's say you're going to call, let's say you only need to find min once. I don't know what I'm doing here. Let's say you only need to find the minimum element of a linked list once. Should you sort it and then return the first element? Is that faster or slower than what we had before, where we ran through the whole thing? What do you guys think? So we have two possibilities. We have sort plus, you know, the head, just return the head. That's one algorithm. Another algorithm is what we had before. This is option 1. Number 1. Option 2 is what we had before, where we just kind of run through the list. Order in. Which one's faster? And so what's interesting, 2 is faster, yeah. But what's interesting is that a lot of people will actually code the first one because it's faster for them to write. You know what I mean? Like sort it and then just return the head. You know, it's a very common thing to do. Like, I don't know how to do something, so I'm going to sort it. Now I know the first element is the min, and I'll deal with it. More interesting question. What if we call min? What if we're going to call min over and over again? What if we constantly want to know what the smallest number is? Like, let's say that this is like a, like, you know, when you go to the grocery store, like if you go to Central Fish, they give you a ticket, you know, and they call, all right, number 52, number 53. And so they're constantly looking up at the screen, seeing what the next number is, the smallest number is. So what if you have to call min m times? So m times you're going to call min. This might even be bigger than n, right? Because like if you're working at Central Fish, they only process one new customer every couple minutes, but maybe you're constantly, like if you're a computer especially, what's the minimum? 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 Oh, it changed. Huh. Announcing number 53. Like if you're writing a program, right? You'll just constantly call, what's the minimum? What's the minimum? What's the minimum? What's the minimum? Oh, it changed. Announcing number 54, right? So which is better now? Which approach is better now? Because here's the thing. You only need to sort it once. Once it's sorted, you can get the min quickly. If you don't have it sorted, you need to run through the whole thing every time. Yeah, we're not inserting or deleting anything. We're just calling min over and over again. Okay. In that case, the amount of work for number 1 is going to be order n log n to sort it, plus you're going to do m heads. Return what's at the head. That makes sense? So you sort it once, you have a one-time cost of sorting it, but then you've sped up all of those operations. Right? You sort it once, and then you can just constantly return the head of the list over and over again. Whereas with this one, if you don't sort it, then every time you try to find the minimum element, you have to run through the entire list over and over again. You got to run through the entire list. And so option 2 would be order m times n. So m times order 1 turns into order. So which one is faster? What do you think? A lot of you are saying option 1 is faster. It's not actually correct. A lot of you are saying now option 2 is faster. That is also not correct. There's no answer. There's no answer to it because we don't know what the relative ratio of M and N are, right? So the question is, how often do you have to do one versus the other? What's the size of the list? How often are you going to be searching for it? Because if you're doing a lot of checking the heads, if M is much bigger than N, then option 1 is clearly the best option. The best option, right? Like if you're going to be getting the head of the list a million times a second, you want it sorted, so all you have to do is head. Here you go. Here. Whereas if, let's say you only call min twice, then it's probably going to be faster not to sort it and to just bite the bullet and just go through the whole linked list twice. You know what I mean? So, life lesson for you guys. A lot of times there is no answer. And what you do is you have to present the options, right? You're like, hey guys, let's have a meeting. Here's what I got. I got one option that is faster when you're calling min a bunch, and I got another option which is faster when you call min not very often. Y'all need to tell me, how often are we going to be calling min? Like, I don't know. Like, I don't know either, man. You know? And so it has to do with how your users are going to be using the code, and a lot of times you don't know that. Are they going to be calling min a lot? I don't know. You know? I can't read the future. And so, yeah. And so basically what you have here is a situation where, we don't really care. Yeah, if M is very big, if M is much greater than N, then N doesn't matter. And you've got, like, let's say it's a trillion. M's a trillion. Then you're comparing a trillion versus a trillion times some number, right? So this will be faster. If M is much smaller than N, then that kind of doesn't matter. And so that's a small number. Log N, what's bigger, log N or M? Right? So if M is smaller than log N, you do this one. Right, do you see that? We have an N here, we have an N here. So the question is, what is smaller, log N, or N? So if M is smaller, we pick this one. If log N is smaller, we pick that one. Okay. So a lot of times these things get complicated by the fact that you don't actually know how people are going to use your program. Right? You just don't know. So you got to guess. And if they misuse your program, then your program will run very slowly. So Muya suggested, as the program is running, to dynamically switch between the two, and that probably is a good idea. So you can kind of monitor the usage of it over time. And all right, fine, we're doing a lot of these. Switch, sort it, switch to the other one. Okay, it's a good idea. You guys understand? Or what else could you do? What other options? What other options are there? Would it be energy efficient? I mean, if somebody's polling you a million times a second, you got to respond to it. Question is, how often do I have to sort? How often do I have to return the next person in line at the grocery store? I don't know. Do a vector sorted. Vectors are faster than linked lists. But in this case, since this is, like let's say these are the tickets at a grocery store, presumably they are going to be able to pop off the front. As person one gets called up, they come off the front of the queue. So in this case, you probably want to use a list rather than a vector. Somebody takes a new ticket. Somebody takes a new ticket. Right. Probably better to use a list than a vector here. What other data structures could we use? Array list. Somebody's a Java programmer. No, in C++ it's called a deck. So you could use a deck for this, sure. A list or a deck would both give similar running times, in terms of big O at least. Stack? Queue data structure? Maybe, but there's always a possibility that somebody gets a ticket that doesn't match. I don't know. Walker, who's taken the class before, knows where I'm going with this lecture. Hashing will be fast. Yeah, hashing will not help us here. So hash tables, the unordered map that we talked about before, won't help us because it does not sort by number at all. Unordered maps will tell you, is 3 in the data structure or is it not? Is 4 in the data structure or is it not? It won't tell you who the minimum list is. To find the minimum element of a hash table is order n. So there is a data structure called a priority queue or heap. So a priority queue is optimized for min element. So it has order 1 min or max. You can have either a min, and this is also called a heap. So you can either have a min heap or a max heap, and whichever one you pick, you get order 1 performance for that. So if you're going to be constantly checking who's next up, you probably want to use a heap. And the good news is you don't have to sort it; it's always sorted. So it's like a binary tree, kind of. It's always sorted. So inserts. So for a priority queue, insert is order logN, as is search, as is delete. All of them are order logN, but what it's optimized for is order 1 min. And so it's probably a topic for next time. I do want to talk about hash tables today, but that's another option, right? So if what you really care about is getting the next person in line, use a priority queue. So a priority queue, you can think of it as a queue, right? Like if you have like a max queue, then as people enter the line, you can have like Bob, who has a priority of 0, and then Sydney enters the queue. She has a priority of 0. This is like the line at the club. This is the club over here. So people are lining up to go into the club, right? And Muya is at priority 0 also. Walker, priority 0. And then we pop, and so Bob comes off the front of the queue. So Bob gets in. And then Kearney walks up, and Kearney, of course, has a priority of 1. And so rather than coming into the end of the queue, Kearney gets to jump to the head of the queue. Okay? But then Kanye walks in. And so Kanye has a priority of 42. So Kanye immediately goes to the front of the queue, and he's going to get in first. Okay? So that's why it's called a priority queue. It keeps things in order, but you assign a priority to them also, and if something has a higher priority, it skips to the head of the line. Okay? It's like at the bank where you've got the business tellers, If you're a business customer, which I am, you get to bypass all the proletariats, like bourgeoisie coming in here, Get my own concierge teller right here. So let's talk about hash tables, because that's really important. So hash tables have really good performance for insert, search, and delete. They're really bad at anything that requires ordering, like this. Min and max, it's not good at. Hash tables, though, hash tables order 1 on average. Insert, search, delete. Very, very fast. If all you're doing is inserting, searching, deleting, use a hash table. That's the answer. They're my favorite data structure. But for things like, let's find the min element. Nope, got to run through the whole thing. Order in, max element, same thing. What about sorting? Sorting is order. Can't do it. You can't sort a hash table. It loses the order. No ordering, so it loses the order things were inserted in. So can't use it for that. But for insert, search, and deletes, hash tables are the boss. So let's see here. Vim main.cc. Let's see here. Don't you. Maybe we'll need you. Okay. So we've talked about set before, right? So set is your, balanced binary search tree. Balanced binary search tree. Now, if we want to have a hash table, we use what is called unordered set, and this is a hash table. Okay, so the interface is pretty similar to a set. You can't have duplicates. You can insert, you can search, you can delete. Sorting is not allowed. These are always sorted. Always sorted. These are never sorted. Can't sort. So what are they looking like? Unordered. Let's just start with a set. Events named BST. And let's do an unordered set events named hash. Might be used. Let's call it H. All right, while true. Read an integer, int x equals read. Type in a number, yo. And then we can do bst.insert to insert the number into the binary search tree. And if we want to insert into the hash table, we say h.insert. Same thing. Interface is basically the same. Okay. So this binary search tree insert is order logN. For the hash table, it is order 1. Very, very fast. Okay. If x break. All right, and then after we've built up this thing, 1 through 5, 6 lines, y6y, shift p, then type in a number to search for, type in a number to insert. Let's actually delete. Let's have a round of deleting things. Erase. Erase. And then we will do one more of these, Y6Y, Shift P, and then we will type the number to search for. We will use count to see if it's in the binary search tree or not. You can use find, but find is just count with more steps because we don't allow duplicates, so who cares? And we're not using the iterator for anything, so just use count in that case. Count returns how many times that number appears in the data structure. So if we insert 50, and then we erase 50, and then count passing in 50, it'll return 0 because it's been erased out. So if it's in there, we will see out X is in the binary search tree. And for that, it is contains. Count should work. Why does count not work? It does work. Okay. Contains works also. So contains is a true or false function. Count returns how many times the object is in the hash table, which is also going to be 0, 1. So shouldn't matter. Okay. So here is a working implementation. Do you guys see how easy it is to use a standard library? Like, do you see how easy it is? Like, rather than you having to make all these like insert functions and pointers and stuff like that, I've actually got 2 different data structures here. This program is twice as complicated as it needs to be, because I'm showing you the difference between set and unordered set, which is to say there is no difference. Right? All the code's the same. But if all you did was change set to be unordered set, then your running times would change from logN to 1. But BSTs are always sorted, hash tables are never sorted. So if you need that, like if you want to be finding the minimum element on a BST is much faster than on a hash table. Why do it yourself if somebody else has done it? Exactly. Just use their code. Their code's probably going to be faster and less buggy too, unless you really get into it. So let's insert numbers: 42, 90, 9,000, 66, 420, 0. Insert some numbers to delete. We'll delete 90 and 66. Insert a number to search for: 42. 42 is both in the BST and the hash table. Search for 420. It's in the BST and the hash table. Search for 66. 66 is not in. And there you go. The most common operations you'll ever do when coding are insert, search, and delete. And if that's all you're doing, then a hash table is your, what is the chef meme? It's, hash tables are great. They're my favorite data structure. I use hash tables more than any other data structure other than vectors. And vectors I use just because just put data into them and read them out later. Hash tables are used if I need something like a database. Like, for example, if you look at my ELO code, one of the reasons why my ELO code is faster than your ELO code is because I am using I'm using a hash table. I'm using an unordered map. We talked about the difference between map and set before. I'm using an unordered map instead of an unordered set. Doesn't really matter. I'm using a hash table, and so that has order 1, insert, search, and delete. But finding the smallest person in the thing might be a little slower. And so just like with vectors, remember how last time we talked about how there's the reserve command where you can secretly allocate more memory? It won't appear any different. Like if you get the size of it, it'll still say, I only have 5 elements in it, even though it's a reserved room for 1,000,000 or 1,000,000,000 or whatever. My size is still 5, but secretly behind the scenes with reserve, what happens is it will allocate that memory so that it doesn't have to do the reallocations. So as you keep inserting into a hash table, the hash table will grow and have to reallocate. And then it'll grow and reallocate and recopy everything over. And so if you know roughly how many people you're going to be processing, then using reserve is a good technique. Okay. So that code allowed me to speed up noticeably over. Actually, let's time it. So let's see, time it. So my code runs in 1.3 seconds. And if I made this a binary search tree, which, let's see if this works. G++, maybe that's a C. Reserve does not work with a binary search tree, of course not. That's it. All the stuff that I was doing there with hash tables, which you don't even know how they work yet, all of the internal workings of all that stuff is now a tree with like pointers and going to the left and going to the right and roots and leaves and balancing and red-black rotations. None of that was being done before, but it's all being done now by changing one word and commenting out the reserve command, which I didn't even really technically need. In fact, let's see what the speed would be with the reserve off. Unordered map. So I'm going to put it back the way it was before. I'm going back to the hash table version, but I'm going to not use reserve. So let's see what difference of time that makes. So you can see by using reserve, it was actually pretty big, 0.3. It's a 25% speed up just from calling reserve. Right? Yeah. So reserve, nice optimization. But I'm now going to switch over to binary search tree mode. And binary search tree mode is 2 seconds, 2.2 seconds. So here you, and so you saw, like, was it 2 lines of code difference, like changing a set to an unordered set or a map to an unordered map and getting rid of the reserve command. So 1.3 seconds without reserve, 1.6, and then in binary search tree mode, 2.1. That's it. So all you guys had to do is get in under 3 seconds. Okay. So that is the beauty of the standard library, is that a lot of these data structures are interchangeable with each other. And so if you just want to try out a different data structure, hey, let's try switching out a vector for a queue, or a deck rather, and see how it changes. You know, let's just benchmark it, because we're doing a few push fronts, not a lot, but decks rather are slower kind of overall, but vectors are slow at pushing at the front. So you just literally change the word vector to queue, and then rerun it and see how the timing is different. That's the beauty of the standard library. It's really nice. Okay, so Mui was like, you're just doing this assignment to flex on your students with hash tables. Well, no. But it does show you guys, you know, by using a hash table, you could take your BST time from 2.2 to 1.6. Okay? On your last homework assignment. So that's the beauty of hash tables. Is there std move between data structures? Yes. Most of the time, though, I don't use std move. And the reason for that is because the optimizer will usually pick up when you can move. And so all of the data structures in the standard library should have move constructors. Unordered set. Constructors for unordered set has a move constructor. So if you have a unordered set, a hash table, and you have another hash table and you're going to copy from it, and then the other guy's going to go away, the optimizer will look at that and be like, not on my watch, and it will call the move constructor, and it will steal the internals of it. And so the new hash table, its pointer to the internal array is going to be pointing at the old guy's internal array. The old guy loses his stuff, he goes away, nothing gets deallocated. And so you can copy all billion elements over in one operation. order 1 operation. So all the standard library containers have move constructors that I can think of. Let's see if Q does. Constructors for Q. Yeah. Yeah, even the queue allows it to move from one queue to another. So, cool. Yeah. 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 So, yeah, it's got that, and then it's got the equals operator. The equals operator has a move. It's got a move assignment operator. That's what that's called. So if you assign the value of one hash table to another hash table, if the optimizer can pick up that the old one's going away, it'll move. It'll move instead of copy. It's nice. It's a nice little optimization. Computer science is neat. Yes, I agree. The standard library is neat. I agree. So in general, like, you won't find me, like, there is a function called std_move. And all that really does, like if you std_move x, is it just turns x into an r value, and r value is, like if you say x is equal to 5, 5 is an r value. An r value is something that can only be found on the right side of the equal sign. Normally y, if you said x equals y, y is an L value, because y could be found on the left side, right? Like you could put y over here if you wanted. And so when you do std_move, all it actually does, when you do std_move, when you do that, all it does is it turns it into an R value, so that the move construct, because normally the move assignment and the move constructor only work on R values, because it's designed for something like this, right? It's designed to be like set Bob equals foo, right? Foo returns a set, and so that's an R value. The value of this you can't have a function on the left side, right? Like you can't say foo equals, doesn't work. And so the move constructor and the move assignment are designed to work in situations like this, and it's guaranteed to work in situations like this, where a function returns a data structure, and then it will move out of it. But the optimizer, like you'll rarely see me. I don't know if I've ever seriously done this. Like tell it move from Cindy into Bob. You usually don't need to do that. And I would almost say it's bad practice to do this, unless your optimizer is just like failing at the job, because the optimizer knows usually better than you if Sydney is getting used after this point. And and so the optimizer will detect when Sydney is going away, and it's safe to move into Bob, and it'll call it. So I don't write code like that. I just write it. I write it like I'm doing a copy. I do that, and then if the optimizer detects it is safe to move, then it will move. Okay. So in general, you don't need to worry about moving or any of that stuff. A lot of people really worry about it, and they shouldn't. The only thing you really need to do is write a move constructor and a move assignment operator if you're playing around with pointers. And that will give you the ability to steal the guts of the other person and speed up your code. All right, so how does a hash table work? Well, a hash table works by being a giant array, like a big array, like we called reserve 10 million. So this has 10 million elements in each direction, and when you insert into it, it doesn't start at the beginning like a vector. What happens is if you're inserting the number 10 million and 42, what happens is it moduluses it by the size of the hash table, 10 million in this case, and so it goes to slot 42 in the array, and it writes it in there. 10 million and 42. Okay? That's in a nutshell. We'll explore this more in Friday's lecture. We'll talk about heaps in Friday's lecture. But the basic idea of a hash table is that you have some value you're going to insert, and you just modulus it by the size of the array, and that's the spot it goes to. If you're going to search, if I'm searching for 10 million and 42, I modulus it by 10 million, check slot 42. If slot 42 is open, false. If it's there, true. The only question is what happens when two different people, 20 million and 42, what if that guy tries writing there? And that's when it gets interesting. So we'll pick that up next time. But if there's no collisions in your hash table at all, then what I presented today is enough. If nobody ever goes into the same bucket, you know, if I were to insert the number 47, 47 modulus 10 million comes into here, bucket 47. If I insert 152, that goes into bucket 152, and so on and so forth. Okay. So that's it. That's all there is to a hash table. You just take whatever value you're trying to insert. If it's a set, the key and the value are the same thing. You just take the value you're trying to insert, modulus it by the size of the array, and go to that spot and write it in. That's it. That's all it is. Insert, search, deletes are very easy until you start talking about collisions, when two of them hit the same spot. Then it gets a little more complicated. That's it. That was the 3-minute explanation of hash tables. Order 1. Boom. That's your spot. Delete. Search. Order 1. If there's no collisions, it's guaranteed order 1. Can you guarantee a hash table as order 1? Yes. If you're going to be inserting ints, just make one bucket for every int possible. So there's only 4 billion-ish. So you make an array of size 4 billion, which takes up, 16 gigs of RAM, no problem. You've got one bucket for every int in existence. Right? Easy. Actually, you can probably compress that down quite a bit, because you only need a true or false at that point. Is the number here? Yep, true. Is it here? Nope. So you can actually do that in 500 megs? 500 megs memory. Yeah. Okay, so that is it for today, guys. We talked mostly about Big O. I've primed you guys for heaps and why we need heaps, because they're optimized for one thing and one thing only, which is binding them in or the max. We talked about how sometimes algorithms don't have a good answers, which is better, because sometimes you got two parameters, right? You got the size of the linked list, and you've got the number of times you're calling an operation on it, and so you can't just directly compare them, right? And then again, we went over balanced versus unbalanced binary search trees, the big O on different trees, different operations, and yeah. So if you guys are interested in the notes that I create, I'll post a copy of them, copy a link. Okay. So there's all my notebooks. Here, guys, take a look at them. Could you go over the CSI roadmap? Registration's coming up, and I'm not sure what to take come fall. Yeah, the typical progression goes like this: 40, 41, 26, 45. Intro to programming, data structures, discrete math, assembly. And then CSI 1 could be taken or not taken. It could be taken kind of at any point. If you want, it's kind of like social issues in computer science and critical thinking and some basic programming. And then also game development, IS-50A, IS-50B. You can kind of take those at any point after CSI 40. Kind of, I guess you could take it before also, but once you've taken 41 in particular, I'd recommend taking 50A and 50B just to get more practice programming, right? And if you like games. You can take IS-50A in the summer. I teach it in the summertime. So that's the progression. 40, 41, 26, 45. Why those numbers exist, I don't know. I would just call them like 1, 2, 3, 4, 5 or something. All right. That's it for today, guys. Thank you. Good luck on Dungeon Delve. If you have any questions, post onto Discord. I'm there 24/7. All right. There isn't 50B of the summer. There is. There is 50B of the summer. I co-teach them. They get taught together. Okay. All right. See ya.